Okay, let's continue. So let's look at the K-means algorithm from another perspective. It's actually a special kind of matrix factorization. So matrix factorization is a very popular paradigm in a number of machine learning problems. For one thing, you can actually do so-called recommendations. So imagine that. So basically, the general idea is that given a matrix X, we want to decompose it into two smaller or simpler matrices. Okay. Um, there are different notions of simplicity. One of the notion is actually rank. Okay, rank is actually sort of intuitively we already know that in linear algebra that we have one important notion uh, is linear combination. And if you think about it naturally applies in solving system of linear equations. So if I give you a condition of x1 plus 2x2 equal to 4, if I give you another thing like 2x2 plus x1 plus 4x2 equals 8, basically they are redundant, right? This is a simple multiplication, but of course, I mean, if you have like a row one, you have another row two, and if row three is two times row one plus three times row two, again, this constraint is actually useless. So rank have a natural important application in solving system of linear equations, and also one of the central things in linear algebra. So rank of a matrix intuitively is actually the maximum number of linearly independent columns, actually the minimum of the two, maximum number of independent columns in the rows, and you take the minimum, right? So basically, uh, rank is a good thing. So for this one, if we assume all the rows and columns are linearly independent, the rank of x is going to be the minimum of n and d, right? And um, so for this one, it will actually be the minimum of n and k, and also k and d. So basically, if you think about the rank on the right hand side, the minimum is actually minimum of n, k, and d. And usually k is chosen to be much smaller than n and d. So basically, it's roughly speaking to be k. Okay, so um, again, this is actually with all the assumptions, but the whole idea is that if I know that k is a small number, this matrix U n times k is not going to have a very large rank, which means not many independent informations, and the same with V. And but their multiplication can give you a very complex matrix, which appears to have lots of information, right? But the whole idea is that the information, if it's equal, it actually means okay, there is not much information there, relatively speaking. But approximate means okay, this x can be this matrix X can be well approximated by some similar matrix X hat, and we can define how similar they are. And basically, X hat is essentially U times V. Okay, so that's the idea. So this is the general idea of the matrix uh, factorization. And in fact, in SVD, we actually talk about any of the matrix using singular value decomposition can be decomposed into three matrices, which is X equal to U sigma V transpose. Okay, where there's a diagonal matrix and the U and the V, the column vectors are actually the basis in the respective space. But anyway, I mean, we focus on the two, I mean, the standard matrix factorization where we decompose a matrix into two. So a, a common way to measure the, um, so this is actually our x hat. The difference between x and x hat is to take some kind of norm. And for matrix, a very widely used norm is called Frobenius norm. And we take it to the square, just easier to deal with. Um, so Frobenius norm is essentially if you X is in general a matrix, right? And you can actually whatever you can concatenate them into a very long vector. Let's say this is our x prime, and then you do the same thing for x hat prime, and then you take the L2 distance. Okay, that's the simplest view. Or you can think about this is essentially sum of using x and x hat, sum of xij for all ij minus x hat ij to the power of 2. So that's the definition. But suffice to say that this kind of Frobenius norm is small, means okay, the x hat is very similar in each and every entry with x. So that's corresponding to a very intuitive notion of similarity or the distance, right? Okay, so now it's a special kind of matrix factorization because actually there are other different kind of constraints, and they lead to factorization results with different kind of properties. One of the things here is that our constraint in k-means is actually very special in the sense that the rows of U must be one-hot encoding. So one-hot encoding actually means we talk about this in the preparation for the clustering. So for categorical values, if there are, let's say, 4 different colors, so we actually use a 4-bit bitmap for each and every value, and you set the corresponding bit to be 1. So only one bit is set. Every other bits are 0. So this U, this is essentially U one-hot encoding essentially says which cluster you belong to. Okay, so if we look at graphically, this is the big X. So we mainly talk about, let's say, if you have, let's say, n times x, essentially x is a column vector, and you actually, x can be interpreted as a bunch of coefficients which combined with columns in n. So this is the case where you actually have a column matrix as multiply a matrix, a column vector multiply a matrix M on the right hand side. But if you have a vector on the left hand side multiply with a matrix, if you still want to have similar interpretations, it's going to be a row vector. Okay, so in this case, you actually look at each row, and essentially 1, 0. For example, the result you can actually see that is just by the shape of it. You can see that essentially each row specifies how you actually combine the rows in the matrix V to form the corresponding matrix in corresponding rows in the matrix X. Actually, this is X hat. Okay, this is approximately is X hat. Otherwise, it's X. Okay, so essentially what you do is that this 1, 0, 0 actually means you take. This actually means 1 copies of C1 vector plus 0 copies of C2 vector plus 0 copy of C3 vector, and this will actually become just C1. Okay, so in other words, this is X, and our X hat is in here. It's sorry, this is C1. Yeah, C1. And if this is 1, 0, 1, 0, this is going to be C2, and maybe this is C3, and this is C1, let's say. Now, the Frobenius norm is essentially take this value and this value, take the L2 norm, right, and sum them together. So it's slightly different from the way we write the cost function in k-means, but they are essentially the same. Okay, you can figure it out. Okay, so in other words, you can see that this is actually the original problem is really to minimize this loss function. And again, this formulation does not give us, better algorithms, but just like in data mining and machine learning, I think it's very important to have different interpretations to look at the same problem from very different angles. And this will greatly deepen your understanding of all the relevant facts. Okay, otherwise your knowledge will actually just be all over the place. Like each one is a separate piece, but you didn't see the connection and their evolution through the time or from different perspectives. So we will talk about EML in a dedicated slide, so we won't talk too much about it. But the general idea is that trying to directly find the u and the v, because we already have this x, now we actually need to find the u and the v. These are the variables we need to optimize, and not to mention that you actually have additional constraints. So it's called a constraint optimization. So this is pretty hard in general. The main reason is that the loss is actually not a convex function. Anyway, um, so one of the methods you can deal with is called the EM algorithm, and basically they do loops. Okay, similar to k-means. K-means is one of the examples. So first of all, you actually do the expectation step. In this example, essentially it says, okay, if I give you the v's, try to find the best use. Okay, and then you actually do maximization. Is that given the use, you actually update trying to find the best v's, and you iterate between u and v. So you can think about, okay, here the parameter is actually, if you treat u as a long vector. So if this is our u, this is our v, you can always stack a matrix into a vector. Basically, this is our parameter, let's say called z. So what you do is that you actually fix part of the z vectors and try to find the best value in the other half. It's not necessarily half, but like the other part. And then you actually, once this is fixed, you actually find the best value for you, and so on and so forth. Okay, and it turns out that there are actually nice property that tells you that it always converges, and it's a very general way to solve a lot of problems. And when we go to the formal slides, you can actually find a more principled way to deal with it, and with a lot of applications to, for example, there is one very fruitful paradigm called the variational inference. Basically, you can think about this as a EM as a very special case of the variational inference. This is a joke I got from some social media websites. But the general idea is that this is basically the chicken and egg problem. So if you can work out one part of the parameter, everything else can be easily determined. But the problem is that each one actually recursively depends on the other one. Right. So the k-means are sensitive to outliers. As we said, we can actually use, for example, instead of using the mean or L2 distance, we can actually use the median or L1 distance. But again, there are still cases where you can't use any objects or I mean coordinates in the space, because it does not necessarily correspond to a real object in the final data set. So one of the things you can do is to change to have further requirements saying, okay, the centroid or the representative must be a valid point. Okay, so it's just like, instead of finding, for example, if you have a group of friends, you can measure their heights, weights, whatever, and you can say, okay, our representative is a hypothetical person, with this height and weight. But I mean, in some cases it helps, but in some cases, I mean, it didn't help. Okay. Instead, what you do is that you actually find the most, you actually find it one real data point in your group which can best represent you. Okay. So this is actually the idea called the Madoids. Okay. So the famous algorithm called the PAM, it's one of the earliest algorithms implemented. Basically, we won't talk too much about the algorithm because it's going to be very slow. The general idea is that you start with some, again, random assignments of the representatives. Here, the representatives are Madoids, and iteratively improve it. So in this case, it's hard to, directly compute which one is the most centrally located. I mean, the most representative one. Again, you have some notion of distance, and you want to minimize the cost of the resulting cluster. So in this case, they actually use some kind of hill climbing or local search based method, trying to iteratively try another proposal and see whether this improves the cost. Okay, the details are a little bit uh, involved. Basically, the actual algorithm have a bunch of optimizations trying to minimize the uh, computation of the overall cost, because every time you only just assign a new objects as the centroid or madoid in a cluster, uh, there are several scenarios. I mean, the newly assigned points could be from the previously from the same cluster or from another cluster, and so on and so forth. So there are different update scenarios to incrementally calculate the cost. But that's the main idea. So it only works for small data sets. So that's why there are different kind of algorithms, mainly based on sampling. So the general idea that you actually sampling is a very effective way, even random sampling, to preserve certain, you know, global statistic of the data set. And for example, if you sample down the 1 million data point to 1,000, then you can comfortably run PAM, and then you get the let's say final, let's say 10 k equal to 10 madoid, and then what you do is that you can actually do further refinement now using 1 million points. Okay, there are lots of improvements, but uh, basically they are still going to be slow, or it will require some kind of hand tuning of the parameters. So this is essentially what we already talked about. Again, previously we mentioned EM is actually, K-means is a special case of EM. It's actually a hard case, and if you relax it to be a soft case, it becomes actually similar to a special version of so-called Gaussian mixture model, where each cluster have the same standard deviation parameter. So basically, the general idea is that if you still remember the U, right, this is the U matrix. Previously, it must be like one hot encoding. Now we actually relax it to be, for example, as we actually say each row is a probability distribution. Okay, by the name of it, it actually means each and every entry should be non-negative. You can't have a negative probability, and they sum up to 1. And basically, you model this one. So given an x, what's the probability you belong to each and every cluster? So if you want, you can actually put xi for each xi, the probability it belongs to Cj. Okay, and so if you sum over all the clusters, that's going to be 1. So we won't talk too much about this one, but basically the algorithms are going to be very similar to EM, except that whenever you do the trying to find the center, now you actually have a probabilistic member, right? So for example, these kind of points previously, it's a hard assignment. So if they all belong to C2, whenever you find the new points, it's just going to be the average of all these points on each and every coordinates. But now each point actually have, this is point 0.8%, 80% of probability belong to C2, maybe 10% belong to C1, and so on and so forth. And this one, for example, this one actually is pretty far away, so it has a great large inference on the centroid. But if this only have zero point 0.2 probability of belong to this center, then basically it don't affect the location of the center too much. So that's the only difference. Okay, now we are ready to move on to the next paradigm of clustering algorithms called the hierarchical clustering. So the general idea of the hierarchical clustering is actually trying to group objects into a hierarchy of clusters. So this actually immediately removed the problem of having to choose a k. So the result will actually be a so-called dendrogram, usually drawn like this. There are different ways. There are actually ways where you draw in this way, especially if you have lots of you know, right. So if you have more guys, you can actually grow downwards. For this one, you need to grow right hand side, which is pretty high. So it's pretty common to see this kind of lie down version of the trees. But the general idea is that now, once you have this kind of dendrogram, you can actually make any cut on the y-axis actually give you, in this case, the y-axis give you a valid clustering. So this actually means this is one cluster, one cluster, one cluster, and one cluster. And this one actually consists of 1, 3, and this one consists of 2, 5, and 4, and 6. Right. So the reason you actually have this kind of branching structure at a different height is because, as you can see, that if you gradually increase the distance threshold, basically intuitively object 1 and 3, which is 1 and 3 here, they actually under the threshold of 0.05. Again, the actual meaning depends on the actual algorithm you use, but roughly speaking, within this limit, they are similar, right? So they all, in other words, they are actually the most similar pair at that time. So you actually merge them into one cluster. So that's why if you cut here, you actually the only singular cluster is actually 1 and 3. So here are some of the advantages of hierarchical clustering. Again, the good thing that you don't need to assume any particular number of clusters, and they naturally form a dendrogram, which is very useful because that's a natural way to organize knowledge, or we actually sometimes call it a taxonomy, or sometimes we call it ontology. So especially in biological sequences. In fact, I mean, for the COVID virus, essentially they actually do these kind of things, hierarchical clustering, and can identify, okay, how the because if you take the virus DNA from each and every patient, basically you can trace out who is most likely to be where did you get the for example, from the patient 32 you actually contract the virus, right? I think that's the way they actually find there is one person who I think spread the virus from bring the virus to Italy from Germany. So that's the way they find it out. So hierarchical clustering, there are two major paradigms. One is actually this is bottom up. So one is actually bottom up, and this is top down. So bottom up is that you start with every point as individual clusters, and then each time you merge the closest pair of clusters until there is only one left. Okay, that's the most common one, and you can actually do a divisive one. This appears to be more efficient, but it turns out that actually most of the algorithms are still based on this one because for agglomerative ones, it's easy to take into consideration the finer details. For top-down ones, as long as you make the wrong decision at the very top without really carefully looking at the details, then you might have some problem. But anyway, I mean, we focus on the so-called agglomerative hierarchical clustering. So sometimes we actually call it HAC, hierarchical agglomerative clustering. So we are going to talk about different variants of the algorithm. They all have the same paradigm. They differ by using different kind of ways to measure who are the closest pair of clusters. Okay, but once they calculated a measure of either similarity or distance, they always choose the closest pair. Okay, the difference is mainly in how you compute a measure between any two clusters, and hence you can always find the closest one to merge at the next step, which is essentially here, right? And again, conceptually, it's actually very simple once you get it. The input can be a so-called proximity matrix, basically, which is actually a matrix of distance. I mean, to pairwise distances. That's actually what we mentioned in the as one of the input format of the clustering algorithm. Another one is that you can actually replace this by a similarity matrix, where each entry is actually a pairwise similarities. So usually distance is a notion of dissimilarity, and so basically if 2 points are similar, they should have a high similarity value and they should have a low distance value, okay, or dissimilarity value. And every time this is always fixed, you always choose the closest clusters. But this part is different for different algorithms. How do you update the matrix? Because once you, as you will see, once you merge the two clusters, you need to update either the proximity or distance of the newly formed cluster with all the existing ones or the similarity values. Okay, so just give you a graphic example in the sense that you already have you start with everybody in, so you have P1 up to P5, let's say you still have other points. Then gradually, in the general case, they are going to form into clusters, right? So let's say they form into 5 clusters. So the matrix is going to be 5 times 5. Now we are going to choose two to merge, okay? But no matter which two you choose to merge, the matrix need to be updated so that it actually becomes 4 times 4, right? Because the new, let's say if you decide to merge C2 and C5 into C, actually you're at 25, it's not 25, but it because we only work on small example, this is easy to see. Then basically you have C1, now you don't have C2, right? You have C3 and the C4, and then maybe you put C25 here. Okay, so that's the idea, and then you do the same thing on the rows. This is, no, actually I do this as well. So you can actually see that the resulting these are the cell entries that are not going to be useful, but most of the algorithm will actually derive the new entry value based on these shaded cell values. Okay, so essentially you need to have this one. For example, you need to calculate what's the similarity or distance between the new cluster formed by C2 union C5 over with C1, and you record the value here. Right? So that's your job. So there are different ways to do that. We let's illustrate the intuition here. So the first thing you can, the essence is that if this is C2 union C5, this is C1. So the general case is that each of the clusters actually contain more than 1 point. If it's always 1 point, it's easy. Okay, the complication is mainly in how to deal with a group of objects. So the simplest way is to say, okay, the two clusters are similar if their closest pair is actually very similar, or the distance is smaller. So the mean actually look at the minimum distance between any 2 points from the two clusters, and use that as the similarity of the two clusters. And the max, so basically mean in this example should be determined by the distance between these 2 points, and the max is the other way around. It actually is a conservative one. So basically it looks at the two most different pairs formed from these two clusters, and use that as the similarity. So it's conservative in the sense that if the max similarity distance between the two clusters is actually still small, it means, let's say 0.7, it means if you randomly sample any 2 points, right, their similarity is going to be at least 0.7, because 0.7 is going to be the furthest, the similarity of the two most different objects from the two clusters respectively, right? And then the other one we use is actually, we talk about the group average first. So the mean and the max suffered from the fact that only one pair of one pair of points from the two clusters determine the similarity or distance between the two clusters. Okay, so it's not reflecting each and everybody's opinion, if you like. So the average version is actually seems to be very easy to understand. is that instead of using only the minimum or maximum, you use the average. So unfortunately, the simple average version have certain glitches. Okay, in the worst case, there are scenarios where it will cause some weird problems. So the so-called group average is a fix. It's very similar to the average. The only difference is that so the average is that you only look into the pairwise pairs. If you can see all the lines, these are the red one. Sorry, yellow ones. But the group average actually means you group the two clusters into one cluster first. So that's the group operation. Then you do the average. Okay. So compared to the simple average, which only take care of the cross cluster, pairs, this one actually also consider these kind of red edges. Okay. So that's the fix. And the central base, the idea is very simple, very similar to k-means in the sense that you compute some kind of representative of the two clusters and use their similarity or distance to characterize the distance of the two clusters. It turns out that under certain similarity functions and representations, essentially documents, the group average and the central base are the same, but they are not always the same. Okay, so in this course we focus on mean, max, and the group average because they are most widely commonly used. Central base is actually easier to deal with, very similar to the k-means. You know how to find the centroid, and what if you have to use data objects as a centroid, right? There are other methods which uses more complex functions. Okay, so let's look at the mean and the first version, and all the other versions are very similar. So although it's actually using the mean, we usually call it a single link, or I think in scikit-learn or in SciPy or whatever, there are clustering libraries, and they actually use just call it a link. Okay, but essentially it's called a single link. We'll talk about the naming later. The reason is that min and max is pretty hard to remember. You have to remember it. The single link and the next one is called complete link. Actually, uses the characteristic or the nature of the algorithm to name it, so it's easy to understand, and there is no confusion. So to further add to the confusion is that whenever we talk about similarity of two clusters, for example, you want to select the most close two clusters to merge. If we are given a distance matrix, okay, distance smaller actually means they are similar. So that's why for distance you actually need to use mean. So that's why we actually call it mean. But just in case I give you the similarity matrix, they already define the similarity between any two points. Basically, you need to use the max. Okay, you can easily reason it out. So basically, if I give you this matrix, right, I don't even need to tell you this is a proximity matrix or distance matrix or similarity matrix. First of all you need to look at is the diagonal entries, right? So it's all 1.0. So by default, all the distance and similarity are normalized between 0 and 1. So P1 and P1, the value is actually 1.0. This cannot be a distance, okay, or at least this is not the ordinary distance we talked about in the very beginning. If you remember, we want the distance function to obey a few rules, and even if they don't obey the metric triangular inequality, but there are, all the precision rules are even more fundamental. Okay, so one of the rules is that it's the distance between the object and itself should be 0. Okay, so basically you can see that this is basically a similarity matrix, and also you can see that it's actually symmetry. Okay, and this is most of the similarity function, and this function we are going to deal with symmetry. So basically, we only need to deal with, let's say, we can actually deal with a triangular part of the matrix. and actually we deal with the upper triangle. So given this matrix, you can easily obtain this matrix, and we just remove all the parts which are not important, right? So this is actually a 5 by 5 matrix, 5 by 5, right? So what we are going to do is to reduce it to be 4 by 4. So this is the beginning of the iteration. What you do, you actually try to find two clusters that are most close to each other. Okay, so since we are using similarity, two clusters are close, it means the similarity is the largest. So that's why we actually choose this one, 0.9. This in turn means we need to merge the P1, P2 into a new cluster. So that's why I write 1, 2 here, and the 3, 4, 5. Okay, but if you think about only this row and this column, again, because of symmetry, we only need to work out these rows, the value need to be updated. Everything else, for example, this value, remove this one. For example, this 0.4 is copied from here because this is the P3 and the P4. This is P3 and the P4. There is no difference, right? We are only merging something, let's say, you are not aware of. I mean, not part of your business. So we essentially can forget about these kind of things, and we just take one example. For example, this one, 0.7. Why it's 0.7? So basically the formula is here, but if you draw a figure, once you are familiar with it, you don't need that. So one cluster is actually 1, 2. So you have P1 and P2. Later I'll just write 1 and 2. And this one only have one guy, which is 3, okay, or P3. So basically there are two links, right, between 1, 3 and 2, 3. So what are the similarity between 1 and 3? So 1 and 3 is this one. This is 0.1, and 2 and 3 are this one, 0.7, 0. Okay, so these are similarities, and in the main, we actually encourage them to merge. So like we are very optimistic. So we actually take the maximum similarity. So that's why you take the maximum of these two values, which give you 0.7, and you do the same thing, and you can get these two. Okay, so basically this 0.65, remove this one. So this 0.65 is going to be the maximum of these two guys, simply because P1, P2 are next to each other. And also the maximum of these two guys become this guy, right? So it's easy to see. So you can draw the corresponding dendrograms, and this is just a sketch, but essentially this will be a similarity value, right? And the first time you actually merge 1, 2 will actually become it's actually at 0.9. So here, if you want to draw it, this is 0.9, and according to the calculation. Oh, by the way, from here to here, you actually do the same calculation. Basically, you are for example, here. Yeah, I haven't finished. Let me finish this one. So basically, from here, you actually have 4 by 4 matrix. Now, then you finish the current iteration, and then you move on to the next iteration, where your goal is to further reduce the cluster by 1. So you are going to obtain a 3 by 3 matrix of similarities. So what you do is that you actually, from the 4 by 4 matrix, you actually find the one with the maximum similarities. That's going to be the most similar pair of clusters, which is 0.8. 0.8 actually means P4 and P5 need to be merged together. So that's why you actually have a 4, 5, right? And by the same token, you actually need to work out everything related to 4, 5, which in this case is actually this cell and this cell. Okay, so you need to work out how you get 0.65. So let me just draw the figure again. So if you want, so how to do the 0.65? It's because you have 1 and 2, and you have 4 and 5, and all the pairwise links are these 4 links. Okay, you look up the value on each and every edge from this table and take the maximum, again because this is similarity. So it turns out that the maximum is 0.65. Okay, I don't have time to explain that for min and max. You can actually get the value and to some extent for the group average as well. You can calculate the value from the previous 4x4 matrix. Okay, you don't need to go through 4 edges, but if you are not sure, because for min and max it's easier, but for the group average it's slightly trickier. It's a weighted version. But if you are not sure, you stick with this sort of slow and stupid method, but it's according to the definition, it's always correct, right? So you look up the value for this one, this one, this one, this one, and take the maximum. It turns out to be 0.65 for this one. If you want to quickly check, this is 1, 2, this is 4, 5. So so let me mark it more clearly. So our job is actually trying to find this guy. This guy is between 4, 5 and 1, 2. So 1, 2 is here and 4, 5 is here. So all you need to do is to find the maximum in this region, which is 0.65. So again, you can generalize this into other cases. So previously, if we draw the similarity, this will actually be 0.9, and the next two merges 1 and 3, which is at 0.8. Okay, so because it's similarity, you are going to, if you relax the threshold on similarity, you are going to see larger and larger clusters. Okay, so it's called the min or the single link in the sense, that's a different way to draw the whole thing. The strength of the min is that it actually can handle non-elliptical shapes. Okay, so the general idea is that, for example, for these two clusters, they are not necessarily circles, but basically they can be joined. They can be clustered correctly into this one and graphically this one. Okay, again, this is still looks like a elliptical, but the general idea that it can be any shape. So you can imagine that if you have points like this, even more contrived shape, they might be able to form a cluster like this. Okay, this is hardly possible. For example, there is another cluster here. Okay, so this is C2. The rest, this one is C1. It's possible to have this kind of shape, but the problem is also that, for example, the previous clusters, they are distinct because there is no noise in between. So if I remove these two, there's no noise in between. So you can see that this part is clear. So there is a clear separation. But as long as you have some kind of noise points here, for example, if you put some kind of sparsely popular noise here, they tend to merge into one cluster. Of course, you have to use two clusters. So basically what they do, again, I cannot see exactly, but I guess it's something like this one and this one. So basically, because the single link, they encourage you to get points from other clusters. So basically, the result might not be intuitive. So basically, whenever you have noise and outliers, the result might be affected. So that's all. We are probably running out of time. So next time we are going to talk about two remaining versions, which are actually very similar to the min or the single link, and then we'll move on to other clustering algorithms. Okay, that's all for today.